So at this point, I believe you guys can develop this theory. First, we talk about triple integrals through a solid. Okay, single integrals along an x-axis or y-axis, for that matter. Single integrals integrate along an axis. Double integrals integrate over an area. Triple integrals integrate through a solid. And of course, we start out with the most simplistic solid, which is a rectangular box. I get a big kick out of the author. I'm going A, B, C, and of course I'm going to go E is less than or equal to Z is less than or equal to A, B, C, D, E, F. And when he goes to S, T, F, what does he go here? R and M or S and T? I'm like, what the?
Well, because E is Euler's constant and F is function of x.
Oh, E is the what constant?
The E is Euler's
Oh,
constant.
E is Euler, yeah. Oh, okay.
And F is used to denote a function.
Oh, I guess that's why he did it. I'm not gonna subscribe to that. I'm not gonna subscribe to that concern.
L is a length, M and N are other units. So you have to go all the way out to.
I'm reading a book and I'm like, what the? Why would you? I have enough trouble with the alphabet. I always was a little kid. I always thought about they were like before the song. They just were like scrambled all up. Thank God for the song. Like there was no order. I can only imagine like all these little letters running all over the place, you know. And then suddenly they invented the song, and oh, thank God, A come B, C, D. Thank God, A, B, C, D, E, F. I had the hardest time with the alphabet. This is the shadow. That's supposed to make it look like it's floating out in space.
It helps.
Yeah, yeah.
A little bit. I was not sick
That's it. So, and you know it's good. So we're interested in going and taking every. Okay, so we have a function. And so W equal F of X, Y, Z is defined on B. Now, what we want to do is we want to think of having the ability to take every single solitary point in here, putting it into that function, adding them up, and getting a total value of F. Just like when we did this in R2. In R2 we had this, right? So we said, well, what we want to do is we want to add up whole bunches of those. We eventually did it by saying it's the integral from A to B of f of x dx. Which is bizarre that it's equal to the antiderivative at B minus the antiderivative at A, but, you know, thank you God. So here, we wanted to do a similar thing. So I'm so worried about like doing too much of this and boring you, but I feel the need to partition AB up into M subintervals, N subintervals, CD into M, and EF into
O subintervals.
No, God forbid.
You want to go alphabetically.
So what we'll do is we'll cut this rascal up. So in there, so yeah, so delta x equals b minus a over n, delta y equals c, d minus c over m, delta z is f minus e over however many I did, n o p q, use r. I don't know why I want to use r. I don't want to use r. So they're all, these are R subintervals. Said before. So we're going to take a random point in this. Now we got a 3D matrix. It's I, J, K location in here somewhere. And I'm skipping a lot of the notation just because I think you understand what I'm doing. That's one cube in there, in this three-dimensional matrix. Yeah? You follow? So in there, we take a random point, x sub I superstar, comma, y sub j superstar, comma, z sub k superstar. Put it into the f function. And then multiply it by its volume and add. And do that for every one of these little chunks. That looks like a, you know, cube. Yeah, that's the, what is it, Rubik's Cube. Yeah, yeah. Okay? So the definition of the triple integral, so I'll give you the definition of the triple integral. The limit as m, n, and k tends towards infinity, the summation, I equal 1 to n, j equal 1 to m, k equal 1 to r of them? R
Working backwards, you can
of f of x sub I superstar, y sub j superstar, z sub k superstar. Now, so this is delta y, delta x, delta z, which we'll call dv or delta v. Okay? So we say that times delta v.
Wait, it's M and K.
So,
There should be a
so,
Okay.
so, mn,
R.
NMR.
Yeah, that's
NMR, right, that's how many of them I got,
Yeah, you wrote
right?
You're okay.
K is the index.
You wrote K under the limit.
Under the limit.
Oh, thank you. R goes to infinity. Nice eye. Good job. So you understand that we're going to take an F value, yeah? And then we're going to multiply it times the volume. So what could that be? Well, F could be a temperature. It could be a sum of all temperature points in the room. It could be a charge. It could be a density again. Okay, it could be a variable density, and we're evaluating the density there and multiplying it times the volume. And James mentioned before, really, in a solid, the volume times the density gives you the mass, right? So we're talking about volume. You said something like area, density, volume.
Yeah, well, volume is kilograms per meters cubed.
Yeah,
So,
exactly.
Yeah.
Exactly. So, in that system. So, that's equal to the triple integral
So volume is equal to density.
over B of f of definitely exist.
So, instead of a line, use a plane.
What's that?
Instead of a line, like, you know, on type 1, use a line, should it use a plane? Or, that makes sense, but like, how would you orientate?
Yeah, that's the tricky part of it, is I usually start out with this as my idea, and then if that doesn't work out, then I have to redraw it and reorientate it. But yeah, if it's totally bounded above by one surface and below by another, but well, right now I haven't gone to non-rectangular regions. But you are right. It would be slices of laminas like this, right?
Yeah, plane.
And then bound it uniquely on each side now, right? By planes, and then yeah,
Damn.
yeah, it's hard to recognize. But
Okay,
you'll
And you create those lamina by stacking those lines together and
create this. Keep going.
yeah, and then you create the solid by stacking those lamina.
That's right. It's exactly right. And the lines are created by
I just stack a bunch of points.
exactly. You see, I have a hard time articulating that. Nice job.